Now, the next bit in Module 4 is nanomaterial synthesis and processing. So, in this, we'll study the methods for creating nanostructures. There are many different ways of creating nanostructures. Of course, nanomolecules, macromolecules, or nanoparticles, or bulky boards, or nanotubes, and so on can be synthesized artificially for certain specific materials. They can also be arranged by methods based on equilibrium or near equilibrium thermodynamics, such as methods of self-organization and self-assembly. Using these methods, synthesized materials can be arranged into useful shapes so that finally the material can be applied to a certain applications. The first one is mechanical grinding method. Mechanical attrition is a type of example of top-down method of synthesis of nanomaterials, where material is processed. Material is prepared not by the cluster assembly but by the structural decomposition of coarser grain structures as a result of several plastic deformation. This has become a popular method to make nanocrystalline materials because of its simplicity and relatively inexpensive equipment needed, and the applicability to essentially the synthesis of all classes of materials. The major advantage is often quoted in the possibility for easily scaling up to a tonnage quantities of materials for various applications. Similarly, the serious problems that are usually cited are contaminations from milling media and or atmosphere, and to consolidate the powder product without coercing the nanocrystalline microstructure. The figure shows schematic representation of the principle of mechanical grinding. Mechanical milling is typically achieved using high energy shaker, planetary ball, or tumbler mills. The energy transferred to the powder from refractory or steel balls depends on the rotational speed, size, and number of balls. The ratio of the balls to powder mass, the time for milling, and milling atmosphere. So, the nanoparticles are produced by the shear action during the grinding. Milling in cryogenic liquids can greatly increase the brittleness of powders, influencing the fracture process. As with any process that produces fine particles, an adequate step to prevent oxidation is necessary. Hence, this process is very restrictive for the production of nano-oxide materials. Since then, it requires that the milling takes place in an inert atmosphere and that the powder particles be handled in an appropriate vacuum system or glow box. This method of synthesis is suitable for producing amorphous or nanocrystalline alloy particles, elemental or compound powders. If mechanical milling imparts sufficient energy to the constituent powders, a homogeneous alloy can be formed based on the energy of milling process and thermodynamic properties of the constituents. Alloy can be rendered amorphous by this processing. Now, the next one is wet chemical synthesis of nanomaterials. In principle, we can classify the wet chemical synthesis of nanomaterials into two broad groups. The top-down method, where a single crystal are etched in an aqueous solution for producing nanomaterials. For example, synthesis of porous silicon by electrochemical etching. Second one is the bottom-up method, consisting of SolGel method, precipitation, etc., where materials containing the desired precursors are mixed in a controlled fashion to form a colloidal solution. Now, in wet chemical synthesis of nanomaterials, we'll study the SolGel process. The SolGel process involves the evaluation of inorganic networks through the formation of colloidal suspension. It's called as solid sol, and the gelation of the sol to form a network continuous liquid phase. This is called as gel. The precursors for synthesizing the media colloidal consist usually of a metal and metalloid elements surrounded by the various reactive reagents. The starting material is processed to form disperably oxides and forms a solid sol in contact with water or diluted acid. Removal of the liquid from the sol yields gel, and the sol or gel transition controls the particle size and shape. Cancellation, calcination of gel produces the oxides. Sol gel processing refers to the hydrolysis and concentrations in alkyl-based precursors such as silicon, tetraethyl, orthosilicate. The SolGel method of synthesizing materials is very popular amongst chemists and is widely employed to prepare oxide materials. The SolGel process can be characterized by a series of distinct steps. So in this figure, you can see the SolGel process of synthesis of nanomaterials, formation of different stable solutions of the alkoxide or solvated metal precursors. Second step, gelination. Gelination results from the formation of an oxide or alcohol bridge network by polycondensation reaction that results in a dramatic increase in the viscosity of the solution. Aging of the gel, during which the polycondensation reactions continue until the gel transfers into solid mass, accompanied by the contraction of gel network and compulsion of solvent from gel process. The third one is the fourth step, that is drying of the gel. When water and other